Hello everybody, my name is Tyler Lay and welcome concrete kings and queens to a magical episode all about admixtures. Yep, we're going to first give you an introduction to admixtures today and then talk about water reducers, an extremely important admixture that we use inside our concrete. Admixtures are a great tool to help us improve our constructability, durability, strength, and economy of our concrete mixtures. They're amazing, amazing things. We're so fortunate to have them. Admixtures are able to extend certain properties of a mix. However, this is really important. It's going to be true for all admixtures. There's only so much they can do. There's only so much extension that can be done. And if you're really relying a lot on chemicals to get the properties that you want, that's kind of dangerous. Okay, so instead, you want to get a concrete mix that's in the ballpark of what you want, closer to what you want, and then use the admixtures to get you exactly what you want. They cannot help the following. They can't help you if you've got poor quality ingredients, if you have incorrect mixture proportions, or if you have poor construction practices. They are magical, but they're not that magical. Okay, they can do you a lot, but if you've got a bad mix to begin with, you're just in trouble. Here are the general types of admixtures, and we're going to talk about all of these admixtures in different videos. There are water reducers, there are retarders, there are accelerators, type A, B, and C. And then they got better water reducers, but they noticed that they retarded a little bit, so they needed a type D. They had another water reducer that would accelerate. That was a type E. Then they got into the superplasticizers. And then the superplasticizer retarders, okay? These F and G are the most commonly used water reducers today. And then there's the good old type S. Anything else they may want an admixture to do, they can put it in a type S. Air entrainment, that falls into ASTM C260. We'll talk about that. Corrosion inhibitors, shrinkage-reducing admixtures, and viscosity modifying agents are all admixtures that are widely used in concrete. But today, we're going to be talking about water reducers primarily. And we're going to go back through history. There are different types. In the 1950s was about the first time people started to introduce water reducers. And there were normal range water reducers. And these are often, a lot of times, waste products from other industries. A lot of times, waste products from the animal processing industry. And this is about how much water reduction you could get. Okay? About 5 to 10%. Okay? Now, then they moved on to mid-range water reducers. Those were a little bit more specialized. Lignosulfonates, okay? These are actually admixtures that are from lignin. You know what lignin is? It's like paper products, like wood products, okay? Then they moved on to hydrocarboxylic acids, okay? These are from the oil industry, okay? Again, waste products. And you would get about 7 to 15% water reduction. And now then they moved into high range, modified lignins, sulfonated naphthalene formaldehydes, okay? These were kind of popular in the early 90s. And then the industry now has moved on to polycarboxylates, carboxylated ethers, okay? And with these, you can get very high water reductions, okay? Up to 30%, and they're pretty awesome. They have taken over the industry. But let's just talk about how do these things work. Now, water reducers are dispersants. They move things apart. Let me tell you what I mean. They don't actually reduce water. They reduce the amount of water that you need to get a certain workability or slump. This allows one to do all kinds of tricks, do all kinds of cool different things. But one thing they can do is they can hold the water-cement ratio constant and reduce the amount of cement. That's one thing I'll talk about. Or you can reduce the water content for the same amount of cement to get a lower water-cement ratio. I'll talk about both of these at the end of the video. Now, cement grains, they actually have an overall charge on them, okay? And when you put them in water, they clump together like this. In water, they kind of flock, is what this is called, or clump. And this makes it harder to mix. It takes more energy to get these to break apart, okay? And this is one reason why our workability isn't quite as high as we would like it to be. And then here comes our friends water reducers to the rescue. The normal and mid-range water reducers, the old school ones, this is how they looked. They were balanced molecules. They had a plus and minus on one side and overall minus on the other side. And they would line themselves up on the surface of the cement grain. Okay? So they would put an overall negative charge on the surface of the cement grain. So if I have a mix with no water reducer, it may look something like this. And a mix with water reducer, it sends those cement grains apart and it makes it easier to mix. Makes it easier to flow. Okay? It's pretty amazing. So this system's going to flow better. It's actually going to also have better strengths because these cement grains are further apart. They're well distributed. So when they grow, they'll grow more evenly, more uniformly throughout. So this will give you better strength. This will also give you lower penetration to outside fluids. So water reducers have become just critical tools to help us produce durable concrete. That's also constructible. That's really important. It used to be in the past that when things got really flowable, the only way to make them flowable was to add more water. Okay, but more water, as we know, is not good for strength, not good for durability. Okay, but the water reducers allowed us to get more workability, to get more constructible concrete that was easier to place, easier to vibrate, easier to finish by using these magical chemicals. But one big challenge with normal water reducers is that the efficiency is limited because they're kind of a low charge per molecule. They're not really optimized to disperse cement grains. Also, the water reduction is non-linear with dosage, so it's kind of hard to predict how things are going to perform. And it also reaches a plateau or a limit, and this is going to limit its effectiveness. Another thing is that these things have a big impact on set time. They slow set time down. They change the surface reaction of the molecules. So what do I mean by this? Well, with these water molecules, with these water reducers, with no dosage, I may have certain slump, but as my dose comes up, it may go something like this. Okay, it's kind of hard to predict what it's actually going to do. You don't know exactly where you're at, and it may be like this. Another one may look something like this. Okay, and it really depended on the cement. Okay, and on the other admixtures in your system. And with set time, the same thing would start to happen. As your dosage went up, your set time would start to go up. So when you started to get near this actual plateau, your set times were so high that it wasn't really constructible concrete because nobody wants to sit around and wait hours for the concrete to get hard, especially if you have some final finishing. If you want to do some final finishing on the surface of the concrete, then you have to sit there and wait and wait and wait. And we're not going to do that. That's not productive. So to address this problem, the admixture industry answered. They said, we're going to change the game. We're going to do things really different. We're going to develop high-range water reducers that have a totally different shaped molecule. This is a polycarboxylate ether, okay? These are a game changer in the world of water reduction. Here's how they work. They're more comb-shaped molecules. They have a large backbone to them, and they have a side chain. So you're able to get a lot more charge per surface area. They can do a better job of covering the actual cement grain, and again, you get a lot more charge. So what's that mean? A lot more dispersion, a lot more of moving things apart from one another. So like I said, the molecular architecture is much more effective. It is a game changer. And the improvement in workability does not have a limit. Well, at least in typical ranges. I'm sure you can get there, but it can really get high water reduction. And these have minimal impact on hydration, minimal impact on set time. So for example, if your slump starts out here, okay, and with dosage you can get extremely high slumps, and with set time, your set time is going to go up with dosage, but it's not going to go up near as high as it would with the other systems. This line is much flatter, and it's linear, so you can at least predict Linear is good. Prediction is good. That's really important. So, like I was saying, this molecular architecture was taken over the water reducer market. It is what everyone uses now. And if you want a little water reduction, then you use a small amount. If you want a high amount, then you use a high dosage. But be careful. Higher dosages of these systems can entrain air. A lot of these polycarboxylates actually contain defoamers. Yeah, that's another admixture that they add to this one to try to make it not produce as many bubbles. Okay, and the bubbles that it produces are coarse, not the ones that we'd like to see. We want fine air void systems. That's not what this system usually makes. So I've been talking about water reducers, but why are they so great again? What is it all about? Well, listen up. This is probably the most important thing I'm going to tell you this entire video. These are the two ways that you can use water reducers, and both are extremely valuable. Number one, you can use it to hold your cement constant in a mix and reduce your water to cement ratio. Let's say that again. You're going to hold your cement constant and you're going to reduce your water content. That's going to reduce your water to cement ratio. And you can do all this by not getting a horrible slump. You can use the water reducer to help disperse the cement grains to still get a satisfactory slump. And this is great. This can allow us to make constructible concrete that we can pump, vibrate, place, and smooth out with lower water cement ratios. This helps us improve durability, strength, sustainability. This is a big, big win, right? Big win. But there's another way to use it. And this way is the most popular way in the industry to truly use a water reducer. You can use it to reduce your paste content. Now, why would that be so popular? Well, paste is your binder plus your water. Your binder is your most expensive part of your concrete. If you can reduce your binder content, you can reduce your costs, okay? And you can do all of this by holding the water cement ratio constant. So let's say I have a mixture that I've designed, that I'm happy with, I'm good with, everything is great, my slump is good, my water cement ratio is where I want it to be. I can reduce my paste content. I can reduce the amount of cement and water, increase the amount of rock and sand, and still get a workable mix, the same workability I had before, but I can save money, a lot of money, okay? And this also still allows us to pay attention to durability and also sustainability, because we're reducing the amount of cement that we use in our concrete. Okay, thanks everybody. Take care.